which is nice, I guess. So hi everybody, my name is Shyamsundar Ranganathan, Shyam for short. It's nice to see a bigger room each year, so welcome to the new folks, and hi to everybody else who was here the last year. So I'm going to talk about RIO. Just like there's still and sparkling water, there are two forms of distribution, DHT and in the future RIO. Yeah. I was getting water and I got sparkling water, so if I wince when I drink, that's because I'm drinking soda. Anyway, so there are two forms of distribution, DHT, and in the future we'll also have RIO. So DHT doesn't go away, but there are going to be two forms of distribution that's going to help different workloads. So this talk is about RIO distribution and reconstructing the onion. So before you start wondering what he's talking about, so the onion metaphor is being used to kind of talk about the cluster volume graph, the translator graph, as various layers in the onion. So we have various translators, and at the heart we have POSIX. So each layer has well-defined abstractions, and there are differences in layers because the core functionality is different, but that's where it differs from an onion. So that's the onion metaphor. But more metaphorically, when you peel apart an onion, it makes you cry. Sometimes when you peel apart the translators, it makes you cry because you're going to think, oh my God, what did I get into? But it's cleansing, you know, at times. At least that's what they tell me. Let's see. So the presentation is really about how do we put the volume graph back as we shift the distribution layer from DHT to RIO. You know, what happens to the volume graph? How does it morph? But before we get into that, let's talk about RIO itself, right? The other part of the title. So RIO actually stands for Relation Inherited Object Distribution. It was also known as DHT2. We'll forget that name after this presentation for the future, but well, it was known as DHT2. So let's talk about relations, inheritance, objects, and start with objects there. So RIO looks at the file system as a set of objects. It classifies these objects into two parts, inode objects and data objects. The inode objects have a further subclassification of file inodes and directory inodes, but for all practical purposes, they're inodes. And so those are the objects that RIO looks at in a given file system. So let's take an example. So let's assume that a user views a particular file system mounted, the root of the file system mounted somewhere in a system at .root, and sees a file and a directory under it, file1 dir1, and under dir1 sees file2 and directory 2. So this is the user view of a file system. Now, RIO views the objects in these file systems. So it has two classes of objects, like I said. So it looks at the inode objects, in this particular case, root, file1 dir1, file2 dir2. And let's just assume file1 and file2 have data, and so there are a couple of data objects as well that it looks at. So these are separated into two sets of objects, inodes and directory inodes, and file data. The relations between these objects are pretty evident. The inode objects are related to their parent inode objects, because they come under a particular parent, and the data objects are related to the file inode objects because they belong to that particular file inode. So if you start drawing the lines out, root points to file1 and dir1, dir1 points to file2 and dir2, and assuming there is data, file1 points to its data blocks and file2 points to its data blocks, right? So these are the object relationships that are formed. Most interestingly, we look at the inheritance, which is what brings about the distribution. So the file inodes inherit location from its, based on its parent inode. So if you look at it, a file is co-located with its parent inode, right? So when it's created, a file and a parent inode will be co-located on the same subvolume or brick. Directory inodes do not inherit this property, and that's why we achieve distribution, because different directories get distributed in different places. Whereas file inodes are, at least in the metadata space, we achieve distribution because we distribute directories rather than distributing the files themselves. The data objects inherit the GFID or the inode hash from the file inode. That's just an easier way to get to the data object rather than having to deal with other forms of addressing the data object. So if we overlay the diagram with subvolumes and bricks, basically file1 belongs under root. So file1 and root belong to the same brick or subvolume, the tiny dark circle there. And file 2 is under dir 1, so that and dir 1 belong to the same subvolume. Now dir 2 is just a coin flip. It could have belonged to either of these two subvolumes, but it just happens to belong to the same subvolume as its parent directory. Not by choice, just happens. Data is distributed differently. It goes to its own subvolumes based on other scheme, because there's no co-location scheme in the data that we look at. We can just simply look at it as a hash of the GFID and then place it wherever we want to. So there are some salient principles in RIO which make it differ from DHT. The first and the most primary being that each directory belongs to a single RIO subvolume. Unlike DHT, where directories belong to all subvolumes, in RIO, a directory belongs to only one subvolume. And so that's pretty evident, because if you really look at it, file inodes are co-located with their parent. Parent needs to be only in one particular place because they're all co-located, so there's no need for the directory to really exist elsewhere in the scheme, in the RIO scheme, right? Further, the file inode and data is separated into separate subvolumes, because as we co-locate files with the inodes with the directory inodes, we cannot co-locate the data in the same place because we would fail to achieve data distribution. So file data and the inode is separated into different subvolumes. This is why we get two rings. We get a metadata ring and we get a data ring. Nothing new, but yeah. So because we have two rings, we have two layouts. And again, unlike DHT, we do not have a layout per directory. We have a common layout for all objects in these two individual rings. So layouts per ring, and it's common to all the objects in those rings. We will not be talking about layouts too much in this presentation. A lot of the layout and layout handling was actually talked about in the last summit. So for those of you in the room who've not looked at that, there's a recording that should probably help. So we'll not talk about layouts much here. All right, so why are we doing RIO? I mean, all this is fine, new distribution, but why do we really need to do it? Vijay actually covered a part of this in his slide deck talking about scale, and that's essentially the point. We are actually trying to improve scalability in Gluster and the distribution layer specifically. So that's one of the key reasons for us to do RIO. The others being, we want to improve consistency handling, want to do consistency handling slightly differently and improve on that, a little bit more on that later. And while doing this, we want to retain the performance characteristics and at times improve the performance characteristics, especially when we get into metadata and such. And we want to kind of see what happens in that space. And based on the layouts, we also want to provide improved rebalance. This kind of very closely links to the layouts. But in short, we want to improve the amount of data that needs to move around the cluster when a rebalance happens, as to the amount of data that's moving around today when rebalance happens in the cluster. That's handled because of more granular layouts, and I'll stop about layouts. So that's RIO distribution in a nutshell. So let's get back to our onion, and let's start looking at the RIO layer in a little more detail. So we talked about scale and consistency. So when it comes to consistency handling, there are a few models that we can adopt. RIO adopts the model of solving the consistency problem on the server side. At least for, not across the entire cluster, but at least within a particular subvolume for RIO. Instead of letting clients lock or fight the consistency problem, we kind of push the consistency problem to the server side of things so that all operations that are related and need consistency handling are funneled to a single point on the server side. So basically we can funnel all entry operations to the parent inode location and ensure consistency in that location. Or we funnel all metadata operations to the inode location, where else, and we can handle the consistency problems arising due to competing operations in there. So what this essentially does to RIO is it splits it into two parts. So there is a RIO client and then there's a RIO server. The RIO client is just responsible for routing the operations. So it sits on the client side, whatever you want to call a client, GFProxy in the future, whatever. It sits on the client side, routes the operations to the right subvolumes, and the server is there to ensure consistency and handle the transactions for certain file operations. And as we talk about transactions come with journals or however you want to call it, some form of journaling. So before we get into the orphan inode and dirty inode for journaling, so in RIO, there are certain transactions that happen. I mean, you need to create the inode, and then you need to link the name to the inode. So that's a two-step operation. Typically in an mkdir, because the directory is not co-located with its parent inode, this is going to happen across two subvolumes. So what if there are failures before the name is linked into the name tree? Basically, you're going to be left with what we call orphan inodes. These inodes are going to exist, they're going to be orphaned, and they need to be cleaned up, or they need to be linked back into the tree, which requires a journal. So that's case A, and those are orphan inodes. And case B is something that I call dirty inodes. Simply put, the inode's dirty, its metadata is dirty, it needs to be flushed back into disk. Right. We'll talk about dirty inodes. We'll revisit dirty inodes in a couple of other slides as well, where we'll kind of talk about why we have dirty inodes and hence why we need to journal them, or why we have dirty inodes at least. We have dirty inodes, so we need to journal them. So for consistency and for journaling needs, RIO is split into two. So now what does this do to the graph, right? So as we shift from DHT to RIO, what happens? So if you take a look at the volume graph today, simplistic view, right? We have some prior accelerators, which are pretty much the caching translators, and then we have DHT, and then we have some other interleaving translators in between, and then we have the client-server protocol, and then all the way we go to the POSIX translator, which talks to the local file system. Typical shortened form of the volume graph. As we introduce RIO, this changes to prior translators talking to RIO client, talking client-server protocol, talking to a RIO server translator on the server side of things before it hits the brick, right? So this is one layer of change that happens because of introducing RIO instead of DHT. Quick note, wherever there are we're going to reuse this diagram a few times in the next few slides. So wherever there are dotted lines, that means there are interleaved translators between the two translators in the diagram. Wherever there's a solid line, it means it's a direct descendant. And a filled up box with bolded text is basically something that's changing in the layer in the diagram. Just a reference in case you missed it. So let's move on. So what else changes? So RIO is not because we don't have directories on all subvolumes in the metadata cluster or the metadata subvolumes. What essentially happens is you don't have a name tree as you see today on the brick. So this basically means our on-disk structure changes. The way we store these inodes, the way we store the data on disk changes. So we have a new disk backend. It's pretty much like .glusterfs, or it's almost equal to .glusterfs with a few changes. I mean, we don't do hard links, we don't do soft links that are present in .glusterfs. So there was a thought that we'd write a new POSIX translator, a new storage backend, and do all this fresh and leave the old one behind, so on and so forth. But interestingly, this is one of the layers which we peeled, and it had a cleansing effect on us, was that we could actually reuse a lot of POSIX. So we found that we could reuse a lot of the existing POSIX translator code for the FD and inode-based operations, just plain reuse, redefining a few macros. And whereas we had to redefine the entry operations because they are different in the existing POSIX translator as compared to what we want in the backend. So we're actually reusing part of POSIX translator work there. But because we're redefining the entry operations, the couple of one enhancement that's already gone in, the GFID to path enhancement that again Vijay referred to, or the entry back pointers, this has to be re-added in the entry operations that we do because we'd be missing that from the existing POSIX code. And we also need these entry back pointers because when we get into handling hard links and rename in the RIO structure, we actually need to kind of go back and see where the file exists, the inode exists, and do the operations from that perspective. The other thing that needs to get added is the UTime accelerator work, which is currently still under review by Rafi. It's posted by Rafi upstream, yeah. So the UTime accelerator solves the time consistency problem across replicas and across different directories in distribute. At least that's what it's intended for. And this is where we revisit dirty inodes again. In RIO, what happens is the time consistency problem is slightly different. There can be data operations that change the A&M times on the data blocks, which is in a different subvolume, say. And there can be metadata operations that change the C time and, on the file inode or the directory inodes. Plus the size and the block information is actually the data subvolume is the one that is authoritative on the size and the blocks usage metadata for that particular inode. So these are actually cached on the metadata servers or the metadata subvolumes on the inode. Now this cache is dirty when there are data operations ongoing, and so we need to kind of keep refreshing that, and that's where dirty inodes come into picture. And the point where utime comes into picture is that when we cache this information, we can no longer rely on the local file system's AMC times or size information. We rather have to store it for ourselves, just like utime storing it for times. We have to extend it for size and whatever else that we need. So we'll need to integrate with the utime work, which is not yet done, but at least we've discussed it as to how we're going to do that. So anyway, this changes the graph very simply, changing POSIX to POSIX2 translator. We're calling it POSIX2 because there is change functionality. So we need to be, the disambiguation has to happen. So we're just naming it POSIX2, but it does reuse a lot of the POSIX code. Okay, I'm going to take a quick break. Any questions? Anything that people are wondering? If not.
Yeah, I would say it seems like splitting up your metadata servers gives you an opportunity at least to use higher speed devices in small file workloads.
Yes, that's true. Sorry, yeah, thank you. So the comment was that splitting out your metadata gives you possibilities of using higher speed devices for the metadata and hence improving performance with that. But I'd also like to say, because there has been a lot of chatter saying, oh, we're distinguishing the two subvolumes. We're doing something different than what Gluster's been doing in the past and such. So it provides that functionality. I would right now say for advanced users, or if we work on our usability and make it so smooth for even the the new users. But otherwise, you don't necessarily have to do that. You can put everything else as is in the same bricks as it exists today. I'm just trying to address another concern that I've heard around the same area. But yes, that's something that we can do, and that's something that we will test and publish numbers with so that it looks good, I guess. So, all right, so moving forward. So we talked about the two rings, right? There is the metadata cluster and the data cluster and the MDC and DC, and in the metadata cluster you have metadata subvolumes, MDS, and data subvolumes, DS. Now the functionality of these two rings are slightly different. I mean, the metadata subvolume is the one that's going to see the entry operations, data subvolume is the one that's going to see the data operations. Some operations are going to be seen by both, like an fsync or setting extended attributes within the cluster stack. But primarily the functionality is different, right? I mean, there is a difference in functionality there. And then if you look at the orphan and dirty inodes, these are things that are pure concerns of the metadata subvolumes. They're of no concern to the data subvolumes. And there's also a reason why the metadata subvolume has to talk to the data subvolumes to refresh its on-disk cache. So there are going to be connections to the data subvolume from metadata subvolumes to refresh its cache. I say all this because the RIO server hence takes two personas. One persona is an MDS and the other persona is a DS, but there is the distinction. And POSIX also takes that to a certain extent, but push comes to shove. If you take a look at the delta of the code, maybe that's just like about 150 lines of code. So, but then at least as a drawing, it looks nice. So, so basically, now what happens is instead of talking to a RIO server, it actually talks to two classes of RIO server endpoints. One is the metadata subvolumes and the other one is the data subvolumes. And the metadata subvolume further is connected to the data subvolume for refreshing its cache, and they talk to their own POSIX layers at the bottommost, as the bottommost layer. So not only are we changing the on-disk format, there are some abstraction changes that are currently assumed across all translators in the stack. The first one being the IAT. IAT is our stat equivalent structure with certain more fields than stat structure. That's passed around the stack. Whenever you look at an inode, whenever you do an inode operation, stat of the pre-post of the parent is passed across. If you're used to NFS protocols, the WCC data that's being passed around is pretty much what we do with our IAT information, when concerned, when we pass pre-post data and all that. But what happens with RIO is that when you do data operations, you cannot get the stat information of the entire inode because it doesn't know about the mode bits, it doesn't know about, I mean, it's not going to keep all that in sync. There's no point. It'll just be too costly. So in terms of performance. So basically, it's the stat data that's going to be returned from data operations is going to be different than stat data that's going to be returned from metadata operations. So we need to call this out more explicitly in the IAT structure, which the IAT structure today does not provide. But there are enhancements proposed for StatX or IAT2, which actually will help us handle this. And if you really look at StatX, it's kind of driven by the NFS and the protocol guys in the Linux kernel side of things. It's actually very helpful because looks like they have similar problems, and it helps us kind of leverage on that and use that to the IAT, what's true in the IAT when we go to the data and the metadata, when we do data and metadata operations respectively. So that's one abstraction. Let's see how that works. The second one, probably a little more controversial, is can we handle anon-FDs at all going forward? So we talked about dirty inodes. So to know, for the metadata server to know that an inode is dirty, somebody has to tell it. We kind of glean that information when a particular file is opened. So we say from open till release, there is no close, it's release, the FD is released, is when the inode's dirty, and at the point of release is where we'll go refresh our cache and put it on disk, and we're done with it. So if you look at that, if you're going to use anon-FDs and go do some data operations directly on the DS, the MDS is not going to know about it, and so it's not going to know about a dirty inode. It's not going to refresh its cache, so all bets are off, which doesn't work. So we end the use of anon-FDs, do something with it. I don't know the answer, but then as it stands, anon-FDs are not going to really work with RIO. Or we treat all inodes as dirty, and that's what the current code does, but that's not efficient either. All right, so no diagrams there, but now let's go, and we've been talking about RIO and the RIO layers and doing that, right? So let's go ahead and add some availability layers to this, confuse the graph a little more. So when I talk about availability layers, I'm primarily talking about replicate and disperse as the availability layers. And I'll be saying that disperse is for data availability only, although it also does metadata, but that's where it stands. So, okay, so it's a little bit of a mashup in this particular slide, but we're talking about consistency in RIO, right? So there's a big jump here to a leader, but what we said was we split it into a client and a server, and the server handles the consistency, and we kind of funnel requests based on inode location to appropriate servers. Now when you throw in replication there, we have more than one location to throw the operation to. Now if you throw it to more than one location, who does, and some operations are transactions, they have to do two operations, like create an inode for a directory somewhere else, come back and link the name in. Who does this? There are three replicas. Which replica does it? We don't know. I mean, all three can't do it because that would not work. So basically on the metadata side, because of the entry operations and other such needs, we are actually looking at a leader-follower model. So we'll have a leader that we talk to, that'll coordinate amongst the followers, and so the leader knows what it does, and the followers are more or less pass-throughs except for maintaining the journals. So this, let's forget about the locking statement there, it'll take time. So basically what this brings into the graph is, it brings in leader election, translator. So there is a proposal out there for a Lex translator, which is extracted out of JBR of sorts. I think Kottresh is kind of more aware of it. The idea is we'll add that to the translator stack. But once you bring in Lex, that's kind of not enough, because as the leader changes, just like GFProxy, you probably need something like DRC to ensure operation continuity, or that duplicate requests are responded to appropriately. So what this does to our, and then one more thing is the, if you really look at it, the metadata subvolumes do not have any data, so they only need replicate, they don't need disperse. Whereas when we go to the data subvolumes, that's where you have data, and so layering it over disperse makes more sense in the data subvolumes. But disperse also does metadata replication today, but basically we just need replication on the metadata side. So what does this do to the graph? So prior translators, RIO client, so far so good. There are two branches, the MDS and the DS side. Let's take the DS side first, it's kind of easier. So the DS side, like I said, we don't need leaders. There is no transactions, there are no journals, there is no funneling operations to a single point. So that can, as today, go to a direct AFR or a dispersed subvolume, which can then go to the client server, and there'll be a RIO DS server piece for whatever for other needs like rebalance and such, and that will go to POSIX. So that part of the branch does not change. Data flows the way it flows today. Except for the RIO client and RIO server bits, but data flows the way it flows today. Metadata, on the other hand, is going to use the leader approach. So what that means is the RIO client is going to talk to a client server protocol which has translator, which is the leader, which will further talk to the metadata subvolume, which will then talk to AFR. And one branch of that will go to local disk, one branch of that will go to client server protocol, which are the followers. And what makes it interesting is there's going to be AFR in the follower stack as well. So there is going to be some work there to kind of make some operations pass through for AFR when it is coming from the leader, rather than, again, replicate it across, because then that will go into a never-ending cycle. But then the whole point of adding leaders changes the graph this way. So if we try to put all this together and extend it across, scale it, we won't go into this diagram, but it's just to give you an idea of, as you scale this, right, as you add more nodes and say I have 5 metadata subvolumes and 25 data subvolumes and such, the graph starts looking like this, and this doesn't even have 5. And this doesn't even represent all the boxes that I've been talking about. But the code handles all of this, so, so anyway. So basically, this is just to kind of say that, as you scale out, this is how it looks. For ease of understanding, you can start looking at the metadata brick processes as something like GFProxy, because it's going to connect to all the other metadata servers and all the data servers, something like GFProxy. I know GFProxy is new, and I think we have a talk on GFProxy in this conference. So, so if you're scratching your head on what's GFProxy, you're covered there. Yeah. So anyway, so let's move on to some thoughts around certain other layers. This is, again, like, a lot of controversial topics in this slide, but anyway. So tier can continue as it is, can go to, unsupported with RIO, or can kind of adapt to RIO, or we can kind of do something better with tier rather than having to replicate the entire metadata structure across the hot and cold tiers as it stands today. Quota completely depends on path-based enforcement of quota, and in RIO on the server side you don't have path-based anything. You're going to do path-based, good luck. I mean, it's going to be very costly, it's not going to be performant. So quota will have to go through a revision, and one of the other contributors, Sanoj, is actually working on something called quota 2 for some other reasons, one of them being RIO as well. Sharding is based on name-based distribution in DHT as it stands today. RIO does GFID-based distribution. What does that mean? Nothing. You give it a new name, it's going to still distribute it. But that's probably not the most efficient way for us to do shards with RIO. So just thinking of ways that we can kind of use the data offset and do the distribution in RIO of data offsets, but leave all the other handling to sharding translator as it exists today. So nascent thoughts around that area of how we're going to adapt sharding to RIO, but let's see how that develops. Broad statement here, GFProxy, which is kind of upcoming, does not need to change much. Maybe we can look at models where you use GFProxy only on the data subvolumes when the number of data subvolumes are far larger than the metadata subvolumes, and just go directly connect to the metadata subvolumes, leaders to the metadata subvolume. But I don't see any risks with GFProxy. Anyway, layers that need to adapt are there. So status, very quickly, we're working on the experimental branch. We're working on the RIO client, RIO server. We're working on the MDS, DS personas for the RIO client and server. We're working on POSIX 2 MDS, DS personas. Kotesh, Sushant and myself are working on this. There are certain abilities supported. From a file system perspective, it's not kind of complete. You can kind of create directories, files, and do data operations, but you can't do directory listings. So the moment you do that, I mean, we've not yet implemented those FOPs, but pretty soon we will. The idea is that we'll release an alpha version with 4.0, and by about 4.1, 4.2, we'll release at least with the availability layers in picture, so that it's usable rather than a toy. It's more usable when the availability layers are added to it. And this is tracked using the issue 243 in GitHub, which is github.com glusterfs 243. The link's there. That gives you an update on what's happening, various documents, design, and such. And that brings me to an end of my presentation. Questions? And I did it on time, apparently. Yeah.
Migration plan from DHT1 to RIO. Data migration or metadata migration, what you say?
Okay, so what's the migration plan between DHT and RIO? That's the question. There is none by choice. No, there is none by choice. That's important. So the thing is, the on-disk formats are different, right? That's what I kind of said earlier on. The on-disk formats are different. So you will have to, you will have to throw in the data from your old cluster to the new cluster, right? So one of the things we're looking at is, for new clusters, of course, we can kind of start at RIO and move forward. There's no migration, but that's not your question. But for older servers, there is consciously no plan. There is no plan to kind of convert on disk into RIO and do such stunts. We don't want to lose data. Those are fraught with dangers.
Instead of asking all the customers to start copying data, I think we should have the smart scripts. We can't simply ask customer to start copying the existing data to new servers, right?
Yes, we can't. But we don't want to mess with their existing. What would you do? Lose data, or tell them to copy data? I would ask them to copy data rather than lose data. Yeah, I'm not saying we will lose data.
Copy data, but with some smart scripts, intelligent scripts, so that it will be faster, not directly CP or rsync.
Yeah. We can work on that. That we'll work on. We'll work on tools, but we're not going to convert data in place. That's what I'm saying. We will not convert data in place.
Yeah, that is
somebody tells me we can and gets it done, fine. But in place migration we're not going to do. Yes.
So as it looks to me, the RIO concept is much more complicated or complex as the HT solution. Does this mean that the consistency problem is way more harder to solve, and this makes the RIO concept a less reliable one than the DHT one?
So one of the rationale for doing RIO is actually to improve consistency. And as we went in, right, leader, follower, and funneling operations and all that, that's actually to simplify consistency handling. So if you ask me right now, I would say with RIO, we actually should get better consistency, and implementing that the implementation complexity of that consistency handling will be much better. But I'm saying that without writing the code. Parts of it is written, but at least on paper, or the design is to simplify the consistency model, not complicate it. We complicate the graph, but we simplify the consistency model.
Okay, thanks.
Okay, so in the interest of time, I'm going to end now. Of course, I'm around for both days outside, and we'll probably have a demo later. Thank you.